All right, well, I will begin with a word of prayer. Everybody who's here is here. I think that's safe to say. Let's see. Dear Father, we thank you for this day again, Lord. I thank you for these students. Just ask you to bless this time we have together to study your creation. Lord, in your name I pray. Amen. So there's a few things on this list of things to do that I have not gotten to yet, and so my out-of-place statement that we were done with parameterizations last class is just nuts. That was based in a world where I hadn't spent all of class on the in-class exercise yesterday. I was still coming to terms with that fact at the end of class. So anyway, getting to it. One of the things we might want to talk about is the concept of collision versus intersection. All right? And, this is kind of an important problem, right? I mean, you have two cars, right? And car A goes from from here to here, right? And start. And car B goes from here to here, start, and do they collide? I don't know, right? Do their paths intersect? Yes, right? See, so collision and intersection are different things, right? Intersection's not such a problem, but so if we want to think about that mathematically, we could say RA of t equals to RB of t gives collision. Right? On the other hand, RA of t equals to RB of, say, S gives intersection. And what I mean to say here more precisely is if there exists some time such that the positions match up at the same time, right? That's collision, rather. If there exists possibly different times, I mean, if you don't like R and S, we could use T1 and T2, Is there a different time? Is there a T1 and a T2 that they both go through the same point, but possibly different times, right? Then that would just be intersection. So, sometimes I ask a question about this. Let's see if we could come up with an example. Suppose that car A goes in a circle. Let's say 3 cosine t, 3 sine t. And let's say that car B goes along the line through the origin with slope 2. And let's do it like this. So what's the speed? What's the speed of car B, by the way? Just a random question, throwing it in there. How would you figure out the speed of B? So I'm chasing a rabbit at the moment. This is my daydreaming bubble. You find the velocity and then calculate the magnitude of the velocity. What's the velocity here for B? One, 2, right? So the speed of B is just the square root of 5. Whatever we're working in, meters per second, feet per year. Well, nobody works in feet per year, right? Maybe people who study tectonics or something. I don't know. Yes? No, I used calculus. I just differentiated. VB is drb dt. So like derivative of t is 1, derivative of 2t, 2. So that's the length of the vector 1, 2. It's the square root of 1 squared plus 2 squared. Good questions. All right, now that I've completely distracted you from the problem, let's go back to the problem at hand. What did I ask? Does car A and car B here, one is going in a circle, one's going in a line, do they collide? Do they intersect? Right? That's the question I'm trying to ask. Let me erase my silly thought bubble and get back on track here. I'll leave it. Let me continue over here. So, which do you guys want to start with, collision or intersection? Collision, all right. Let's see here. So we're looking for 3 cosine t equal to t and 3 sine t equal to 2t. We need both, right? For the position of car A to be equal to the position of car B at a particular time t. So, any ideas? When I see an equation like this, what I would do is I'd divide the bottom equation by the top equation. First of all, t equals to 0 is not a solution. All right, we can ignore t equal to 0. Why is t equals 0 not a solution? T equals to 0, it solves the second equation, but not the first. Right? The first equation, if I put t equal to 0 into it, I got 3 equal to 0, which just isn't true. So t equal to 0 is not the solution. So if t is not equal to 0, in fact, I need cosine of t is not equal to 0. Then I can divide these equations and I get 3 sine t divided by 3 cosine t is equal to 2t over t, right? Which is 2, and the 3's cancel. We get tangent of t equals to 2. And so t is equal to what? Now, is that a solution? I think we could go back up and check, you know. Let's see. I mean, I could use a triangle approach. If the tangent of t is 2, if I put a t here, that means I could put a 2 here and a 1 here. This would be square root of 5, I think. Right? This is a triangle which describes tangent of t equals to 2, opposite side 2, adjacent side 1, hypotenuse square root 5. And if I have that triangle, I can tell you what cosine of t is. What's cosine t? 1 over root 5, yeah? What's sine t? 2 over the square root of 5, yeah? And so I guess my question is, do those solve it? So it's 3 over root 5. I guess the question is, what's t? I need t in terms of I don't know, I need a calculator at this point. I'm sorry, guys. But when you do these sorts of things, it's important to check and make sure you've actually solved both equations, because when we combine equations, sometimes we can inadvertently lose something. And so after we do some simplifications, it's important to take the answer and plug it back in at the initial equations and see it actually works. Yep?
How much do we need to divide 3 sine of t by 3 cosine of t?
Because that eliminates time. Yeah. To eliminate time is why I did that. So this angle t is about 63.43. If I take the cosine of that thing and I multiply it, oh, I'm sorry, I got to do, I need to do radians, right? Well, Yeah, the radians. Dang it. Curses. Where did that thing go? Come on. My calculator is not, it's not helping me. I forgot how to change to radians on my silly calculator. Ah. Curses. Oh, there it is. Radian mode. Inverse tangent of 2, what do we got? 1.107, roughly speaking. And let's see here, what's 3 times the cosine? 3 times the cosine of 1.107 is what? I get 1.342-ish. And, uh-oh. Yeah. So this is not actually solving the problem, is it? Interesting. Does it solve the first one? Huh. Interesting. What's that? Radians, inverse tangent of 2. I think in radians is 1.107. Am I wrong? That was in degrees, but there's no 60. I mean, I should stick with radians, or I should stick with degrees. We can't mix. Listen, let's try something. So this is Desmos, all right? So I think we can look at this directly. We had x equals to 3 cosine t, yeah? Y equals to 3 sine t. Let's see here. I might have to do it like this. There we go. And we're going to let t range from what? Say 0 to, I don't know, 6.3. That'll get us all the way around, right? Now, we could add a slider in here, and then we can make it go all the way around. Or we could even animate the curve, like, fun, huh? All right, and then the other one, it was what? T, 2t. All right, and we probably should go from something like, I don't know, to play around with this a bit, but something like that. Let me actually trace the circle out here. So obviously there are what? There are points of intersection, right? How could we look and see if there's if there's a point of collision? Well, one way you could do it would be just to match these sliders up, right? let me mess with this a bit. We really just want a to go from what? -3 to 3, you guys think? All right, let's try that. I said go. Go. What? No go? Oh, look, we can't. -3 is hard. Let's. It doesn't make sense. We can't go from 0 to -3 for the t interval, right? So maybe we should go from, say, 0 to 3, something like that. Still crashing it. Curses. Yeah, let's make that go. I don't know. Some tinkering is required, right? Come on. Son of a gun. Is it step setting? I don't think it's steps. I think. Oh, you're very, very good point. 0. That would explain it, wouldn't it? Thank you. Oh, that was close. Oh, I think we have an intersection, but not a collision. You can see it, right? So, and I'm not sure how I have seduced us with wrong algebra today, but something's wrong about the algebra that we did, right? And like I said, we should double check after you do some manipulation. You should, go and see if it actually does solve both equations at the same time. Now, another approach to the intersection problem is to fall back on earlier means, right? If I had, for example, R of A equal to, I don't know, let's say t e to the t, right? And if I had RB of t equal to, oh, I don't know, cosh t, sinh t, something like that. And suppose I'm just asking intersections. One approach I could take would be to reduce it to a problem of Cartesian coordinates, like find the corresponding Cartesian equations for these, and then just look for a simultaneous solution set. Right? Forget about the time altogether. And so, like, this is what? Yeah, that's y equals e to the x, right? The first one is that. And what's the second one? We have x equals cosh t, y equals to sinh t. So together we have x squared minus y squared equals to 1. So you know what these look like, right? That's a hyperbola which does what? Yeah, I guess my question is, does that open upward or sideways? What's it? Sideways? If I put y equal, yeah, I think you're right. If I put y equals to, no, if I put y equals to 0, I get x is plus or minus 1. Okay, yeah, I believe you. You guys told me sideways. I believe it. Very good. I was just checking. I always try to check plugging in where I say I can't cross, right? I'm saying that there's no x equals 0 solution, which makes sense to me, because if I put x equal to 0 here, I get minus y squared equals to 1, which is, there's no real solution for, right? Which is how I know it opens sideways. I mean, there's other various approaches, but that's one. So this is that, right? And what's y equals e to the x look like? Yeah. because x is equal to t. So I eliminated the time to find the corresponding Cartesian equation. That's all. That's all. Nothing too funny going on here. So this graph is, of course, the exponential, right? Now, I can't tell you what that point of intersection is precisely, but I can definitely tell you that there is a point of intersection, right? Where is it? You see it? It's right there, right? I'm pretty sure that's the only point of intersection. So if I was testing for collision, then I would just need to probe whether or not these two paths actually get close to each other, close to that time. Anyway, that's pretty much all I know about collision and intersection, so there you go. I mean, generally speaking, these are really hard problems to solve because you're asking, possibly nonlinear, a system of possibly nonlinear equations in two variables. Do you know how to solve those in general? I mean, I don't. So these problems in the wild are pretty difficult. And if I just make one up, we won't be able to solve it. I'm not at all surprised that there was no point of collision for this. I would have been flabbergasted if we actually had a point. If we had a point of collision for this, it would have been like a miracle. All right? So, very unusual.
Sort of a silly question, but if there's a point of collision, that automatically means the intersection.
That is true, yes. Collision implies intersection. But not vice versa. Yeah. Uh-oh, yep. So moving on, we had other things to do in here. So suppose you had a guy, use your imagination here. You've got a giant, all right? And he's got a yo-yo. And he's swinging it round and round. Somehow on this yo-yo, there is a platform that allows a little dude to stand horizontally. And on that little platform, little dude on the horizontal platform, it's always horizontal, he is also having a yo-yo, which he is twirling. Then the question is, what's the path that the little dude's yo-yo takes as it goes through space? I mean, I can draw kind of a picture for this. I mean, you're like, could you come up with a less ridiculous example? I suppose I could. But here's little dude, and of course, use your imagination. And so this is his. I don't know. I tried. So the point is, he's got a yo-yo, and he's swinging it round and round. Now, forget about this. I give up. But the picture would be something like this. Right? I mean, that would be if if suppose it was at night, it was dark, all you could see was the yo-yo, and the yo-yo happened to have a light in it. You just see this weirdo path, right? And how would you come up with, say, a parameterization for something like that? Like what could you use? The answer is actually relatively simple. What you want to do with this sort of thing, if you know where it's coming from, you can decompose the motion into a sum of other things. So what I would do for this sort of problem is I would, somewhere there's an origin. And so this is the position, let's say, from the giant, Rg of t, right? And then relative to this, there's a position relative to the origin for the little dude, so L of t. And so to get to the yo-yo from the origin of the background, you just add those, right? So to get the net displacement, we just use R of t equals to Ra of t plus ROA. Listen to me. G for giant, L for little dude of t, like so. So specifically, let me be more specific here. Suppose that, as advertised, we have a circle. So say r cosine t, r sine t, yeah? And the position for the little dude is also a circle. Let's say little a cosine t, little b sine t. I can add those two things together. What's the net position going to give me? Did I use A and B? What would A and B do? That would give me like an ellipse. If I choose different values here and here, that ends up describing an ellipse. So I wanted to put an A on both sides because I was trying to keep it simple. Relatively simple. I mean, both circles, okay? Now, the fun thing is, we can actually picture this with Desmos without a lot of work. All right? And I can adjust even. I'm going to make my, let's see here. Get rid of that. So what I want is A cosine t plus r cosine t a sine t plus r. We're not looking at anything we should be yet. Let's try that again. There we go. Actually, do I have it? Is it? Oh, we can't see it, can we? Now, what's still wrong about my picture? See, really, the little one should be going much faster, right? So to make it go much faster, let's say 10. So making the yo-yo shorter or longer. And then, of course, we can make the giant make it yo-yo faster. Eh? Eh. So, I guess if you ever see a pattern like that in the sky, you should probably think there's like a giant and like another little dude and like a yo-yo or something. Maybe not. You know, in the time before cell phones, not your parents, but perhaps my parents, they used to amuse themselves by making patterns like this on paper. Can you imagine such a time? It's true. There's like a little thing you can buy with like gears, put a pencil in it. Yeah. What's that called? A spiro what? Yeah, spirograph. There you go. All right. I think we have. So one thing you could do if you're stuck on a problem is just to throw it in here and play with it for a minute to try to see if your algebra is completely off base or not, right? Now, you know, can I test on Desmos? Not really. Does that mean I don't care about it? Doesn't mean I don't care about it, right? I can't test everything I care about. shouldn't assume that just because a professor doesn't test on something, it doesn't mean they don't care about it. Sorry, I've been arguing with people on the internet lately. Anyway, so this should help you with that very difficult sounding problem about the thing upon the thing, right? Now, what problem is that? 6, yeah. The other thing I should mention is, generically speaking, we have the following freedom. We could do like this. R of t is equal to something like r cosine of omega t plus delta, comma, r sine of omega t plus delta. So you can choose omega and delta and r to give various setups, types of circles. Now what you know, if we had omega t equal to 2 pi, what would that make t? I mean, if you think about it, if omega t equals to 2 pi, that defines big T being the period. See, when that omega t term cycles through 2 pi worth of radians, that means that your sinusoid has gone full cycle. So this omega is also 2 pi over the period. It's called the angular frequency. When I put the omega in the thing on the board equal to 100, that means that if we're working in units of seconds, it's going to go like an angular frequency of 100 radians per second, right? If I just put t there, it's a radian per second, right? Oftentimes, we just make our parameterization have an angular speed of 1 by default. But you have the freedom to adjust it if you want it to go faster for some reason. That would especially be relevant, say, in an application, right, where you're trying to engineer something that needs to have a speed other than 1 radian per second, right? These are things you can adjust to achieve the kind of circular motion you're interested in. All right, enough about that. I have other things I'm supposed to talk about today. If I could find my markers. Let's see here. Yes? Well, delta has to do with the starting point. So if you put in times 0, you'd be at r cosine delta, sine r sine delta. So like if at time 0, I want to be here, then that would be something like r cosine delta, r sine delta. So you want to pick the phase angle. This delta is usually called the phase angle. Yeah, phase angle. You want to pick the phase angle to match with your starting point. We could do that. Radius of the circle. Yeah. So I should mention colliding and intersecting, right? One further comment about that is if r of t gives path, then at t equals to t naught 1, we could write the parameterization of the tangent line to be L of t is equal to r of t naught plus r prime, plus t times r prime of t naught. Let me just take a second here to try to demystify that formula for you. If we drew a picture of the path, it would look something like, I don't know, maybe this. So let's suppose that the point we're talking about is, I don't know, right there. So the origin is somewhere. But wherever it is, we go from the origin out to there, that would give me r of t naught, right? Suppose that the path is right moving, so it's going this way. What's the velocity vector look like to that? Well, something like this, right? So that would be r prime of t naught. What's the tangent line look like? It's the line with the direction vector of the velocity, right? So if I was to do it in green, it would look something like this, right? So what I'm asking the question at the moment is, how should we parameterize the tangent line? So one answer to that is that this gives a parameterization of the tangent line, what I wrote down here. This parameterizes the tangent line. Do you see why? See, because I start out by adding the base point. I go from the origin out to here. And then I add a scalar multiple of the velocity vector, right? And that just traces out along the tangent line. As t is positive, we're like over here. If t is negative, we're back here. And that's a parameterization of the tangent line. But my question to you would be, is this a intersecting or a colliding? Are these paths intersecting or colliding? I think it depends on what t sub 0 is, right? Let's suppose that t sub 0 is not 0. If I could graph it, it would be something like this. Maybe t equal to 0, I'm right here on the blue line. T equal to 0, I'm right here on the green line. And see what happens? They're not colliding, right? Unless t sub 0 is equal to 0, these are merely intersecting at the point of tangency, and maybe somewhere else, but they're not colliding. If you want the equation for the colliding tangent line, it's very simple. Instead, we parameterize it like this. We take the base point, and then we just do t minus t naught times the velocity. See, then, if you look at the colliding parameterization that I just wrote down, you plug in time 0, what do you get? That, when we plug in time 0 into t minus t0, we get 0. 0 times a vector is 0. And so we just have L of t naught equals to R of t naught. And so they collide. This is the parameterization for the colliding tangent line, if you wanted to make it collide. Oops. Well, hopefully you've already done this. So I think I have some homework questions about this. It's not a big deal, but there it is. So I think I've covered most of the questions that I've posed on the worksheet, right? But there's one that stands out to me that I haven't yet really fully discussed in here, which is arc length, right? And I don't think I have quite enough time to derive the arc length integral today. I'll save that for some other day. It's in chapter 13 in my notes. It's about a page. It involves the mean value theorem. Some other time we'll do that, okay? At the moment, I just want to remind you what we know about arc length and just emphasize the main calculations, okay? Let me put this away. So if I have some path, right, and I think about a little arc length along that, you could call that ds. And so a kind of heuristic picture there is to look at this as being dx and that as being dy. So most of you would agree with me that ds squared is equal to dx squared plus dy squared. And then if you're, if you bought this much, well, let me do more. So divide by dt squared. That gives us ds dt squared equals to dx dt squared plus dy dt squared. So apparently ds squared is equal to dx dt squared plus dy dt squared all times dt squared, right? I'm getting to the point here. So we can think of ds as being the square root of dx dt squared plus dy dt squared. Now what I'm doing right now is in some sense formal nonsense. I actually have a way of deriving this in a more careful sense, but this is actually a very good mnemonic just to think about arc length and as it relates to the parameterized curve. This is the formula for the infinitesimal arc length. How do you find the whole arc length? You just add these up, all right? So to, for path with t1 less than or equal to t less than or equal to t2, we calculate the arc length as the integral from t1 to t2 of the square root of dx dt squared plus dy dt squared dt. Now I have to be very careful here. Almost anything I write down, we will not be able to do this integral with our current technology, all right? In fact, for many curves, it's always the case that we need to use a numerical method to do this integral, truth be told. But I do have one example that's important that I can do for us. So I could look at the x equals to r cosine t, y equals to r sine t path for, say, 0 less than or equal to t less than or equal to 2 pi. This is somewhat famous. We have talked a fair amount about this already. This is a circle with radius r, right? So let's calculate the arc length for a circle. So S is the integral from 0 to 2 pi of the square root of what? Minus r sine t quantity squared plus r cosine t quantity squared dt. What does that, almost off the rim. So what is inside the square root simplify to? You've got an r squared, we've got an r squared, we can factor out the r squared, then that gives us a cosine squared plus sine squared, which is 1, right? We're assuming here, by the way, I'm assuming r is positive. So, yes?
Why is y equals r sine t? Why did it become negative instead of integral?
This is, so they're not, it's not x, it's dx dt, and it's dy dt, so yeah. That's fine, no problem. So long story short, this is nothing more than r dt. This is r dt, all right? And so we're just integrating r dt from 0 to 2 pi, and so that gives us 2 pi r. The circumference of a circle is 2 pi r. But there's another thing we can do with arc length. We can talk about the surface area of a curve of revolution. So talk about that briefly here. So the idea is simply this. You have some kind of curve, all right? And you rotate it around the x-axis, let's say, right? And so this rotated around the x-axis gives you some kind of, you can't draw it worth anything, like this. And the question is, what's the surface area? So what we do is we take that surface and we divide it up into little bands like this, right? And so what's the surface area of one of these little bands? Well, it's got ds along here, right? And this is the radius. So the little bit of area for that one band would be 2 pi times the radius. What's the radius here? Well, the radius would be the y for the curve, right? Y is the radius for this. So we do 2 pi y ds. So this is, and then add these up. So if this curve is parameterized, if the point here, is x of t, y of t, again, for t1 less than t2, the surface area would be equal to the integral from t1 to t2 of 2 pi y, well, ds, but what is ds? It's the square root of dx dt squared plus dy dt squared. So this is the formula for surface area of a curve of revolution, a surface of revolution. Again, one example, then I'll stop. If we were to take, say, the half circle, which would be what? Take the half circle, which would be from 0 less than or equal to t less than or equal to pi. We've already calculated in my last example that ds is r dt. So therefore, the surface area of this surface of revolution would be the integral from 0 to pi. My y is r sine t, and then I've got r dt. So this gives me r squared minus r squared cosine t, evaluated from 0 to pi, which is what? And what did I miss? There's a 2 pi in the formula for surface area, right? So I neglected that down here. So what we've got is minus 2 pi r squared times the cosine of pi minus the cosine of 0, also known as minus 2 times pi r squared. There you go. 4 pi r squared is the surface area of a what? A sphere, right. So the parametric viewpoint makes these sorts of calculations not that bad. Now, beware, that's about as much as I want to do right now. We'll come back to some more of these maybe once we have some more integration skill. If I've asked you to calculate it in the homework, it might be that you're supposed to wait until you know the integration that we're about to learn over the next week. So starting tomorrow, we will start doing those things that you've heard about from other sections, this integration by parts that you've heard speak of. And at this point, starting tomorrow, everyone in every other section will become an amazing tutor for you, because they've already been integrating parts by parts for a solid week, right? So, but anyway, I shut up. Thanks, guys.